Hi again. We have two more reactions that are an extension of the Aldol reaction that we've learned before. The first one we'll look at right now is the mixed, or some textbooks call it the crossed Aldol. And then the second one is a so-called directed Aldol. I believe we are up to reaction D, and I'm just going to call it a mixed Aldol. If you think back to our first three reactions, A, B, and C, aldol, aldol condensation, and intramolecular aldol, we only had one main starting material, and it either reacted with another one of itself or it reacted within itself, like the intramolecular aldol. You'll notice in this case, for a mixed aldol, it's mixed because we're going to use two different molecules, two different aldehydes, or an aldehyde and a ketone. In this first example that I want to try, we're going to mix this aldehyde, butanal, plus benzaldehyde. And to keep track of these molecules, as I talk about them, I'm going to label them A and B. Molecule A, molecule B. We want to run an aldol, and we're going to do a deprotonation at the alpha carbon. So we have some base, we need a proton source, and in this case, we could either use heat or no heat. Why don't we practice using heat and try to figure out what the product is after condensation, after the heat does the dehydration. Now, you might think that, oh no, we have two molecules. How do we know which one is the enolate and which one is the one being attacked? Or does it matter? It definitely does matter, but we set it up very nicely because look at this benzaldehyde over here. This has no alpha hydrogens. What that means is that this molecule, the benzaldehyde, cannot be the enolate. You can't deprotonate this carbon. So this is not the enolate. Let's check the other molecule, the butanal. Butanal has an alpha carbon right here that can be deprotonated. So this is the only choice for it to be the enolate in this reaction. Becomes enolate. All right, so visualize, put yourself in the round bottom flask, and let's say you use this base, sodium hydroxide, and you deprotonate a small percentage of this to make the enolate. Well, now we have to decide who is it going to attack. Is it going to attack the benzaldehyde, carbonyl carbon here? Or is it going to find another one of itself and attack that? The trick is, and it has to do with the setup of the reaction, we can do this in high yield to get only one product. And the way you do that is you have to choose something to be in the round bottom flask and partner to be in a separatory funnel. But we're going to use a separatory funnel to drip, 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 solution something, either A or B, into A or B. Well, we want to assure that the enolate attacks benzaldehyde. That's what makes most sense, right? Why would we have these two molecules if we didn't want them to combine together? Okay, we don't want it, I think it's obvious, butanal to attack itself. Okay, or else we wouldn't have this benzaldehyde here. So the design of the experiment is, how do I ensure that anytime an enolate is made, that it's going to bump into a benzaldehyde? We're going to ensure that by putting the benzaldehyde in the round bottom flask at high concentrations. Let me double check that. Yes. So we're going to put B in high concentration. Okay. And that makes this be A. Where should we put the base? Do you realize if we put the base up here, then A will become an enolate and then will start attacking itself. But if I put the base down here, B with the base is safe, because there's no just no alpha proton to remove. So I want also here plus the NaOH. Let's make this green. So as you're dripping A into B, can you see that once that drop of A, and it's dissolved in water, so we can make it dilute if we want, but there's so much B that when A hits the solution of B, the base is going to deprotonate A, and the chances of it hitting another A are going to be pretty minuscule. You're going to spin this, or you're going to stir this very fast by spinning a magnetic stir bar super fast. So those drops are dissolved almost instantaneously. And now A will get deprotonated and it will be surrounded by a bunch of B. That's how you run this reaction to ensure that A will attack B. Now that we know that, you could do your scratch work if you want, or you don't have to. I think some of you now can see without drawing these pseudo mechanisms, right? Dotted arrows, what's attaching to what. But what was the trick? The trick is, again, I like to have my alpha carbon right there on the right hand side. Okay, I know that's my attacker, or at least I know that's where the connection to the aldehyde is going to be, at that alpha carbon. Now, let's be a little bit careful because we have heat. Okay, so I'm not going to draw the hydroxyl group here, which I would normally do if I'm doing the aldol product, but I'm really making the aldol condensation product. What I can do is realize what is attached to that dot. A hydrogen and a benzene ring. Now, I'm not going to draw the hydrogen, and I'm going to try to decide where I want the benzene ring, but it's a little bit hard to decide which one is more stable. Have the benzene ring up or the benzene ring to the right. Let me just put it to the right, like this, okay? And now remember what happens with the condensation? You make a double bond, if you can, between the alpha and the beta. And how do we tell if we can? We can tell if there's a hydrogen here. That's the hydrogen we're going to remove along with the OH that was right here to make a double bond right here. Okay. Now what's interesting about using benzaldehyde as one of our partners is that not only do you have conjugation to the left, you have conjugation to the right. So this is highly conjugated. And to tell you the truth, highly conjugated systems are so stable that it may not even be necessary to use heat to push the reaction. So I'm going to say here highly conjugated, and it probably didn't need the heat. It probably did not need heat. What that means is it might have been very hard for us to just get the aldol product. Remember, the aldol product is the one with the beta hydroxy group. Even if we don't have heat, it may be hard to stop the reaction because it's so wanting, so motivated to make this double bond to get both sides of the molecule conjugated. Okay. So that's a cool trick. The trick is have one of the partners not have an alpha hydrogen. Okay. The other trick is to understand that when you run this reaction, you are doing a slow addition. This is called slow addition, to ensure that anytime the enolate is made, it is surrounded by the benzaldehyde, and that's where it's most likely going to attack. For practical purposes on an exam, am I going to say all of this, or am I just going to write this and ask you to draw me the product? If you see two different carbonyl compounds, you will have to assume that I want to do a mixed aldol and have no mixtures, right? I don't want A to attack A and A to attack B. You're going to assume that since I'm giving you A and B, I want those two to react with each other, okay? Without me explicitly saying that we're doing this type of setup. So what are some other This is great, this benzaldehyde. What are some other carbonyl compounds that don't have an alpha hydrogen? So other carbonyls, okay, without alpha H. We're going to list them because these are nice to have in our back pocket if we want to do a mixed aldol. Okay, these will be safe because these will be good partners because they don't have any alpha hydrogens and they cannot be the enolate. Okay, formaldehyde. We already have benzaldehyde for the example. Another kind of unusual one, but it is popular. This is called furfural. F-U-R-F-U-R-A-L. It's an aldehyde. And the last one is, yeah, this one has no alpha hydrogen also. 2,2-dimethylpropanol. Okay, looks like a tert-butyl group. Okay, those are great candidates for mixed or, again, some textbooks call this crossed. Okay. All right. Reaction E. There's another way to do a combination of two different carbonyl compounds, and that's called a direct aldol. Reaction 9E. Direct or directed aldol. I believe this is our last aldol reaction, but even the reactions after this, reaction 9E, they're very aldol-like, except we're now going to use different molecules besides aldehydes and ketones. Don't worry about that. I'm not even sure why I even mentioned it. Let's finish this directed aldol. Do you recall that, let's do a little bit of acid-base chemistry. Do you recall that if I have maybe this ketone, or let's use this ketone. It didn't matter, but I just want to make it a little bit bigger. That we actually have an equilibrium between the enolate and the neutral version. And you know how I like to draw the enolate? I like to draw the enolate in the form where the O is negative. Okay, but this still means, right, that the alpha carbon was deprotonated, right? We have two hydrogens here, and we have only one hydrogen here. It's just that the resonance structure, this is a major contributor. But do you recall that your conjugate acid is H2O? Okay. In terms of pKa's, I remember that this is around 15.5. And this one, I'm going to cheat. We talked about it in the first video. It's a ketone, maybe 20-ish. Uh-oh. Give me 1 second. Oh, right, 20. Okay, pop quiz. If this was a ether, if this was an ester, would that go up or down? The pKa for ester is actually a little bit higher. A little bit higher. Aldehyde would be a little bit lower. That's video 1. But because of this pKa difference, do you notice that it's mostly this? This is the side that's favored. Equilibrium favors the weaker acid. That's great, because all we want to do is have a little bit of the enolate and then have it react with the neutral aldehyde or ketone. So that's great for an aldol. You'd need a percentage that's has an enolate and a percentage that's not enolate. But directed is a little bit more, well, I'm going to say direct, because now I'm going to use a very strong base, LDA. I'll show you what LDA is in just a bit. Lithium diisopropylamine. Let's form that enolate, again, the same enolate, and the conjugate acid, not water this time. LDA is lithium diisopropyl amine. So there's your amine part. Here's your diisopropyl part. And in the base form, it was N-. But when we picked up that hydrogen, it becomes NH. Okay, so it's an amine. The conjugate acid is an amine. What are your pKa's? The pKa for an amine is 36. Is that going to make a difference? Mm-hmm. Yes, it will. Because now this is the weaker acid, this side. And actually, it's so much weaker. Yeah, 16 pKa units. This is only a 4.5 pKa unit difference. This is so much weaker that we essentially are going to claim that we get 100%. Not only 100%, but 100% right away, because this is a strong base. That leads us to a, what? A weak conjugate acid. Equilibrium arrow is very much to the right. See, that's a problem if you're just doing a regular aldol, because now we have 0% of this very quickly. Okay, we make the enolate instantaneously. For all practice and for all intents and purposes, we have none of this. We can't do an aldol, but what can we do? We could take this enolate and then add another carbonyl compound and do the aldol reaction on that compound. So here's the strategy. This is why that pKa of 20 is so cool, because for some bases that you know, we get just a little bit of the enolate. For other bases, we get 100% of the enolate. And you are going to use LDA to do this type of reaction, called a directed aldol. Okay, so here is the sequence. I have this ketone. Okay, so it could be a ketone or aldehyde. It has to have an alpha hydrogen for sure. First, you're going to do LDA to make 100% of the enolate. And then number 2, you're going to give us another carbonyl group. And it could have its own alpha hydrogen. It doesn't really matter because we already made the enolate. So, I don't know. Now, I'm freezing up. Let's just do this. I'm trying to decide whether we're going to do a condensation or not. Let's go for it and see what happens. And heat. Okay. This is your attacker, and you know what I like to do. I like to draw the attacker so the alpha carbon is ready to attack. I have attack to the dot, which is now this dot right here. I want to do a condensation, so let me just draw what's connected to the dot. Connected to the dot is an isopropyl group and a hydrogen, but I'm not going to draw the hydrogen. I do know that this alpha carbon still has a hydrogen to be removed, and that's what we're going to do. See, for the aldol, there would be an OH right here. But I'm thinking ahead because I want to do a condensation, or the problem is telling me to do a condensation. Boom. Okay. That is a good aldol condensation product because it's alpha beta. Remember this? Alpha beta unsaturated, in this case a ketone. But also, it's like a mixed aldol, except now we're not worried about getting different combinations because we're making 100% of the enolate via LDA. Oh, let's do one more. This will be, I'll ask you to pause the video. Let's do this. I'm wondering if you all can get this one. LDA. Oh, interesting. Let's use that ketone. And let's say no heat. Now, if I don't write heat here, you're going to assume that you're just making the aldol product, unless you have this really weird situation, not weird, but this cool situation where you can form conjugation on both sides by putting the double bond. Again, this was the example where I really don't think you need heat. And I'm pretty sure you don't need heat, actually, for this reaction. Okay, we could have left off the triangle and get this product. Let's have no heat. Okay, and I'll just not draw the triangle. Can you draw me the product, the Aldol product? Go ahead and pause the video, get your guess here, mark up your page if you need to with a bunch of notes, and then come back, unpause the video, and we could double check. Okay. The enolate is going to be formed between that cyclohexanone and lithium diisopropylamine at that alpha carbon. The trick is to draw your attacker as is and attack this dot. That dot is this dot right here. I don't have to play games and pretend there was an OH here. I should draw the OH because there's no heat. So I am making the beta hydroxy ketone. What else is connected to the dot? Two alpha groups. That's your product. Alpha, beta. So here we have a beta hydroxy ketone for the aldol product. And this is now just to complete this aldol condensation. Okay. And double check, alpha beta unsaturated ketone. Okay. All right. It's still a mixed, well, it's a mixed aldol, but now we're using LDA that has a special name, directed aldol, because we're making 100% of the enolate via the proper use of this base right here. Well, I do have 7 minutes left, and let me give you a like a synthesis problem or a retrosynthesis problem. And the idea is this. Here's a molecule. This is going to be hard at first, or I imagine this is going to be difficult at first. How do you make that? I think this could be made via one of our aldol reactions because, see, here's an alpha and here's a beta. Uh-oh. Did I already make this? Aw, man. Okay, we'll use this. Shoot. How do we make this? Comes from. So this arrow, the one that's bigger and open-ended, that's a retrosynthetic arrow, and which means comes from. Can't believe I chose this example. But this is my thinking. That alpha was the attacker. So this carbon-carbon bond must have been made. That's my attacker right there, where the enolate was this molecule here. Now, I am visualizing, I hesitated to say, but I am visualizing an anion right here that attacks this dot right here. But remember, in the mechanism, I like to make the enolate the O anion. Okay. But for this purpose, yeah, go ahead and pretend there's a negative charge here that attacked this dot. What had to be on the dot for it to be attacked? There had to be a carbonyl group. Okay. Your combination would be this, I think. That plus this molecule, which would have been the enolate. And see, imagine the C minus here attacking here. Or, better yet, because I like to draw the enolate with the O minus, imagine that. So this became that, okay? This is going to be a crossed aldol, most likely. And then you have this mechanism that goes like this, that hits up there. Okay. Now, because it's very, very conjugated, I don't think we need any heat to do this dehydration. Let me give you another example, something that we haven't seen. Okay, how about this one? I don't know if this is going to be crossed or just a regular aldol. We'll decide. I'm getting this from a textbook, actually, and here they made it a little bit trickier because they abbreviated the aldehyde group. Let me just put here example 1, example 2. Okay. Where did this come from? Well, the first thing I would do is I would redraw it. Many of you don't need to redraw this, but I have trouble seeing the aldehyde without redrawing it. Okay. Okay, we're going to do the same analysis up here, down here. This is your alpha carbon, right? It's the one, it has to go alpha beta, right? So the carbonyl, then the carbon next to it is the alpha, this is the beta. That's where the double bond is being made, between the alpha and beta. So my two molecules are the stuff on the left and the stuff on the right. For this carbon here to be attacked by the enolate, it had to have been originally a carbonyl. How many carbons is that? 1, 2, 3, 4, 5, 6, 7, 8. And here's your dot. But what about my attacker? My attacker is also 1, 2, 3, 4, 5, 6, 7, 8. This attacked itself. So you can test, or you can give this to a friend. Ask your friend what molecule you get if you do this reaction. Because my contention is that it looks like it's an 8 plus 8. You could take a, I don't know why I have so many cocktail napkins. You could take a cocktail napkin and you could say that was the enolate. Envision a C minus right here that attacked another carbonyl group that had this many carbons with a carbonyl group right at the dot. And when you think about that and draw out those two molecules, they're actually the same molecule. Very good. Let me just make up something random. I won't do this with you, but you'll do this on your own. Oh, did I mess up already? Oh, man. Give me 1 second. It's not as easy as I thought it'd be. How about... Oh, sorry. How about that? Okay. And the other thing is, I didn't formally draw a proper reaction. This is just like the strategy, right? This reaction here would give me this product. So I imagine, or I predict that this would be the main product if I do this. When you give me when you try this one out, man, I really hope this is correct. Alpha. Either you could do a mixed aldol, but I think you should play it safe, actually. Because now that I look at this, I think both partners could be the enolate. So why don't you do a directed aldol? Take one of your partners, right? Take one of your partners, choose the one that you want to be the enolate, and react it with LDA. And then bring in the second partner after all of that has turned into the enolate. And that would be the strategy. All right. I'll put this problem on the practice problems for this video, and I'll get those answer keys worked on soon. But try this, okay? You have your notes for reactions A, B, C, D, and E. See what you can do to make this molecule. Hint, it's an alpha beta unsaturated ketone, so you know you're doing a condensation.